Uh, Good morning, everyone. I do hope my voice is coming in loud and clear. Yes, right. So, I'm sorry, yesterday the entire lecture couldn't be recorded because there were issues with the storage services associated with IIT JWebEx, but I do hope there were no issues with it because the slides and the material and everything was shared. So please do feel free to get back to us if you have any questions or doubts or would like to discuss uh, anything. Please feel free to do that. You can write to the TAs, you can write to me, no problem. Okay, so right. So till yesterday, what we were doing is reinforcement learning. So now from the next three classes, which is today, and the next two, which is in the next week, I'll try to cover a topic called probabilistic reasoning over time. Okay, we'll be moving a little further, or we'll be just taking our Bayesian networks to the next level. You've all done Bayesian networks, basic probabilistic reasoning. I suppose you've all done that. Yeah, fine. So this is just trying to build Bayesian networks that grow with time. Okay, so kind of modeling a dynamic environment. That is what we wish to do, but it's very difficult. It's rather difficult to model a dynamic environment, and pretty much if you again the same questions that were there for reinforcement learning, the same questions come over here as well. You are trying to predict something. Excuse me. You're trying in this entire model of probabilistic reasoning. You are trying to model, or you're trying to predict a future state from certain observations or again certain predictions you have made in the past. Okay. So you have a set of state variables, you have a set of evidence variables, but how much of that is true, how much of that actually models the situation you are in, those are all subject to questions, right? So that is why we have different kinds of strategies. This class, I'll actually be introducing the topic of probabilistic reasoning. And in the next two classes, we'll be doing different techniques that come under probabilistic reasoning over time. Okay. And as usual, at 9, there'll be a quiz. So I'll try as much as I can in this class. So going back to work, we're trying to model a very dynamic system. We're trying to predict what the next state is going to be from observations that we have made in the past, from predictions that we have made in the past. Now, how much of that is actually modeling the real world? That is subject to question, just like I just said that a couple of minutes ago. But still, that doesn't stop us from making predictions, even in the real world. We were functioning. Yes. Okay. We can function without knowing probabilistic reasoning in mathematical terms. We can very well survive in the world without that. But when you're trying to design an autonomous system, or your job is that of an analyst, then perhaps these different models come into play. That is when you actually apply these. Okay. And then what happens is, this is my understanding of the job. You predict something, you do something. If it works out, fine. If it doesn't, then you can again go back and revisit some of your thoughts. You can change certain things that you thought were to be true. You can do that with a certain amount of confidence associated with it. So basically, whatever we are doing in this particular topic of artificial intelligence too, they're all based on some form of probabilistic reasoning. isn't it? In reinforcement learning as well, we had it in a big way. So now I'll be sharing my slides. I suppose everyone has access to the slides. I just shared it about half an hour ago. Yeah. So, right. And these slides are all from Norvik's book. Okay, I haven't put in anything extra except a few questions that I keep pondering over, and I would encourage everyone else to ponder over as well. And there are another set of slides, which is the resources slides. I haven't shared this with you right now, but I will share it at the end of this class. Okay. So this is the set of slides that I have for the class. So as usual, the first slide is kind of a premise of the story that I was just saying so far. That you have a partially observable environment. Basically, every environment in the real world is partially observable. So how do we kind of model the actions that are possible in this environment? We can't do an it's very difficult to model everything that is possible in the environment. So we kind of make a trade-off. We make a choice of a number of parameters or the number of variables that we would like to concentrate upon. And if it is a dynamic environment, our variables too are going to change. So now many questions come up with that. Many interesting questions, and in the course of this class, I'll ask you to think upon them, and then maybe that could lead to a thesis or maybe new ideas coming from you. And let's see, it's not that everything that we think has to lead to a paper. It's not at all like that. Just thinking and being creative is fine as well. Okay. So, right. So now you have a partially observable environment. Like I said, almost every environment is partially observable. So now what do we try to do is keep a track of the current state as a function of the sensors from which we collect all the data, as well as the past states. Okay, the past states are again a combination of a transition model. A transition model, just like in reinforcement learning, is some kind of a representation of what can happen next. And we have a set of sensory percepts of what you gather from the external world. And usually in all textbooks, not in papers, in textbooks, we talk about the external world, the external sensory inputs. But we must remember that when you're trying to design an intelligent agent, a completely intelligent agent, you must also make allowances for sensor inputs from the system itself. Okay. Because if you're learning, if you think about it, if you are learning, the sensor inputs just as much as they are from the external world, which is your observations, they are from your internal world as well, which is from your knowledge repository or your experiences. Okay, so in textbooks, you will mostly be finding sensor inputs as external inputs, but we should also consider the internal inputs as well. And you could actually, in real-time systems that are deployed in the real world, the ones that we have all around us, they collect data from sensors, actual sensors. Okay, just like we do. We have our eyes, we have our hands, and we have so many things happening. Fine. So transition and sensor models may be uncertain because here again we are involved with predictions. We are trying to look at the future, or maybe based on what we have observed of what has happened in the past, our predictions in the past, and we keep moving back and forth in correcting our predictions, in smoothening our predictions, in clarifying our doubts. This is what we keep doing. We take a step forward and then we move again backwards. So we can never be certain about our transition and sensor models as well. Okay, so just like I mentioned a couple of minutes ago, the probabilistic reasoning over time is a way of designing Bayesian networks that grow with time. Okay, we are not talking about the ones that are just fixed for life. And again, model dynamic environments, disease progressions, population growth predictions, work habit predictions. These things like work habit predictions, cultural predictions, these are coming up in a big way these days with human interfaces being built, human machine interfaces, and then human factors or the user design environment that is so big these days. This is where work habit predictions, cultural predictions, um, and other such features come into play. We kind of mix um, psychology, a bit of psychology, a bit of sociology into whatever we do these days. Okay. So now the world is viewed as a sequence of time slices or snapshots. This is essentially, if any of you have come from the core computer sciences, you will know that it's all about digitizing the analog world. So we must take samples. So we again view the world as a sequence of time slices or snapshots, each of which comprises a set of random variables, some observable and some not. These set of observable states are, we represent them as X. You are free to use any variable. This is just the convention that's followed in the book. So we have a set of unobservable state variables which define the condition of the agent at some time t, and we have a set of observable evidence variables. The evidence variables derive from the sensor inputs. Okay, and we have XAB. X, this is rather small. This is XA to B actually. There's a colon in between A and B to kind of define the state variables from time A to time B. Okay, since we are dealing with networks that grow with time, and I'll come to this slide a little later on. We have orders of Markov models, right? We have the first order Markov model, we have second order Markov model till the nth order maybe. So, and in each of these models, each of these orders, it all depends on how many of the previous states do I consider in order to build up a prediction or in order to come up to a new state. Okay, so if I consider just one state, I have a first order model. If I consider two previous states, I have a second order model, and so on. So in order to define the order, this is where this A to B comes into question. Okay, how many previous states do I consider in my in order to predict the next state? Okay, so here is an example. We have healthy, if XTB, whether I am healthy or not. This and whether the observable states are temperature, heart rate, blood oxygen levels, respiration rates, and so on and so forth. So if I use these sensor inputs, a combination of these sensor inputs, a combination of values of these sensor inputs like temperature, heart rate, blood oxygen level, blood pressure level, blood sugar level, and etc. There's so many parameters. I can come to a conclusion whether a person is healthy or not, right? It doesn't have to be as crisp as healthy or not. It can be healthy, extremely healthy, partially healthy, not very healthy, and different grades of healthiness based on these parameters. And here time is again of consequence because the time over here again, the granularity could be over 1 day. You keep measuring these parameters all across the day, which is perhaps in the morning, in the afternoon, after an activity, before an activity, after eating, before eating, right? The format. Okay, okay. I'm so sorry. I didn't notice this. I'm so sorry. I'll do that. Yeah. Right. Is this better? Yeah. So, right. So where was I? Yes. So now the time that we consider over here, we will have different granularities to consider whether you want to measure these parameters over the course of one day, which is in the morning, in the afternoon, before food, after food, whatever. And you can also take it over a longitudinal time in the sense of number of days, months, and years. Okay. So if it's for a singular person, you might think about one day, each day at a time. But if you think about the world at large, then you might consider it over a larger time span. So the granularity is up to you depending on the problem that you're trying to model. The state variables as well are dependent on the model that or the problem that you are trying to model, and so are the evidence variables, because the evidence variables are a function of the sensor capabilities, whether you have real life sensors to actually capture the data of the real world, or or the conditions that you are trying to consider in order to build up a prediction of some kind of your system state. Okay, so everything over here is a variable. Then the number is a variable. Fine. So now, for ease of our modeling purposes, we consider that the same set of variables are observable at each time slice. That means if I want to observe a person as healthy, I will keep considering all these different parameters at the same time. Okay. Temperature, heart rate, blood oxygen, respiration rate, blood pressure. I consider all of them together. But that is not exactly how the real world works, or at times it may not be necessary to actually count each of these variables. It's not necessary. Fine, but for ease of modeling, we'll consider them all. So now my question to you, if I come up from here, I would like to see your thoughts. Can you think of the kind of data structures and knowledge activation protocols that you might want to model this dynamic kind of a system where all variables may not be available, uh, or may not be activated at every time instant? Okay, I would like to leave this question with you actually to ponder over and contemplate over. Because I'll just give you a small example. This is an example I keep using in classes, in other classes as well. Because, for example, I know none of you, I haven't seen any of you in person, but I might have spoken to you, right? I might have talked to you. I may have talked to you on the phone. I may have had a meeting with you. So my only input about you is your auditory input, right? So I listen to you. I I collect statistics of your voice, the way your voice modulates, the pitch, the frequency, etc., and many other such terms. And so I have. Uh, so you are unobserved to me, right? You are partially unobserved to me. So I build up some kind of a visualization in my mind about you, just based upon your auditory input. And again, if I want to extrapolate this a little, if there's someone with a heavy voice, I might, with a baritone kind of a voice, I might picture you to be a very tall person and huge, and someone with a very a lighter kind of a voice, I might think you to be on the thinner side. Okay, this again I do because I have my experience statistics connect me in those lines. Okay, so this is a large network that is coming up, but it helps me build up some kind of a model of you. Okay, since I haven't seen you in person, so what do I have is just the auditory input. Let's say, hoping the world gets better, and you arrive on campus, and then I have multi-sensory inputs about you. Right, I get to see you. I get to perhaps if we shake hands, I get a tactile input as well. So it's a combination of inputs coming in. And if you see, my number of variables also changes. My model of you changes, which was earlier just a predicted visual model and an auditory model. I now have a actual visual model of you. I have a tactile input as well, because different people have different ways of shaking hands, right? So this small environment of just me interacting with you has such a lot of dynamicity embedded in it, right? So now, can you think of the kind of what shall I say, dynamic data structures as well as knowledge activation protocols that you might want to design if you were to model such a system? Imagining that you are trying to design an autonomous agent, a social autonomous agent. If you're trying to do that, then this is just a question. I will put them in prison. I just came up over here. I came out of the presentation mode to see if any of you would write questions or write your thoughts in for the question. Right. I'll go back to presentation mode. Right. So this is what our model comprises of: states and observations. And now we come to our transition and sensor models. This is all what a probabilistic reasoning model over time would look like. Okay, so we have a Bayesian network that is growing with time. The first diagram over here that you see is a first order Markov model. Why? Because we are just concerned with the state that is the one that is before me. Okay, and this is an order 2 Markov model because I'm considering a little more. In order to arrive at this prediction, I take in 2 more inputs. Okay, so this is a second order Markov model. This is a first order Markov model. And this is how it all looks like. And here the question again is the time that you are going to consider. If I go to the previous slide, you see here is the time. And over here, I have a set of observations and a set of variables coming up. So for how long should I consider my time? Here it says a finite number of states. Again, finite is countably infinite, right? So there are many such questions that come up when you're actually going to model this system. So for ease of computation, we always do a trade-off wherever it be. So we say the current state depends on only a finite number, just a countable number. You can extend this to anything actually. You can extend this to time series. You can do that. This is just a preliminary idea of what it is all about. Okay. So now, a second order Markov process would look like this, but the definition over here, if this were the equation of a first order Markov process, you see it's dependent on only one variable, the one that just happened at the last variable. If t is my current time, just t minus 1. But if it were to be a second order Markov model, how do you think you would modify this equation? Can anyone, I'll just come out of this presentation mode. And any thoughts? If this particular equation, I ask you to represent a second order Markov process, what do you think would go into this equation to make it a second order Markov process? Right, those could be, but we will just put a right that the one that I just received now, that is a more a generic representation. Right. This one, the one that I just see on chat right now. That is a more generic representation, but what it ultimately looks like, that is a different question altogether. How you come to this probability, that is a different question altogether, but just the generic representation would be, there would be an xt minus 2 coming into question over here, right? Just the generic representation. So now the question over here is, we are considering a variable with time t is again another variable in the question. So how long do we consider our variables are dynamic? So what do? Is we again do a trade-off over here. And we have one trade-off over here, finite number of previous states. And another trade-off that we do over here is, right, exactly. The another trade-off that we do is we consider the world as stationary, not static. Okay, static means nothing changes. It's just the same thing that you see today and tomorrow. But we just consider the world as stationary for the sake of operational purposes. Stationary meaning that the number of variables don't change. Right, it is being recorded. Yesterday's session 2 was recorded, but not it couldn't be recorded entirely. Hopefully today's will work. So over here, the problem or the trade-off that we do is we consider a stationary number of variables. You see, it's just x and e, or a certain number of x variables and a certain number of e variables. Certain number of x's and certain number of e's. Okay, so here it's very important to consider it's a stationary world with respect to number of variables, not a static world. If it was static, we would not be doing probabilistic reasoning over time. Okay. And again, another, just for operational purposes, we consider that the conditional probability of all events is the same across all t. So what happens over here is you just have to remember two conditional probabilities. One is for the start state and one is just for all the other variables that you are considering. Just one for the start, the one which is at time t0, and for the others. And for all the others, if you maintain for operational purposes, so the conditional probability is the same. So it's just two values that you are remembering. Okay. So, right. So this is how it looks like. This is a transition model because we're just considering our unobserved states. Then we come to the sensor model, which is considering how our evidence variables will look like. So now these evidence variables, they draw in from, they should ideally draw in from the states as well as previous evidences. Sorry, they should be doing that. But again, for a first order Markov process, we just look at the state. Just look at the state. Ideally, it should be an arrow over here as well as something that comes in from the previous evidences as well. That is the ideal equation, but just for representational purposes of a first order Markov assumption, we assume that my states contain all the information that is necessary in order to arrive at but to kind of these, actually, if you think about it, the inferences in the opposite level. Okay, so this is this particular example of rain and umbrella. This is what I took in from Norvik's book. What they say is the problem that they are considering is you are a security guard positioned at a place where you can only see umbrellas and predict that whether it's raining or not. Okay, a very simple problem, not a very realistic one, but a very simple problem. So the question is, if I see an umbrella, I know that it's a rain condition. Okay, so the inference is in the opposite direction, but this is just to show the dependability. Because in the event that happens is if it is raining, then only will the umbrella go up. That is from the actor's perspective, but me as someone who is trying to understand what the actor is doing or is trying to understand what the real world or what is happening in the real world, my understanding is in the opposite direction. Right. So now the umbrella condition could be because of sunshine as well, but I am only considering just one variable over here or one condition, which is rain. Okay. So that is why I have two states. It's either raining or it is not. T meaning it is raining and F meaning it is not raining. So this is my first state. So I have a conditional probability associated with that. And over here, these are my other conditions, another true false. So if it has rained and if I have an umbrella over here, so my predictions go up. Okay, these are my conditional probabilities that I hold for all the other states, not just one state. It's for t plus 1. I will hold the same kind of probabilities just for operational ease, nothing else. Okay. So This is just a rough idea of what a first order Markov model will look like, or a first order uh, a simple Bayesian network will look like. Just a very simple one. So now when we move on to higher orders, when we try to bring in more dependabilities, we bring in connections here, we bring in other connections as well, then this is going to kind of expand into this very complicated model. Okay. But the basic assumptions will remain the same. That is, the number of variables, we are not actually thinking about adding to my variable repository in order to build this network. Okay. Right. So now the natural question at this juncture is, how should I fix my my probability at this stage? How should I fix that? That question is never answered anywhere because that is something you just assume. You just start with it. Okay, it's like what shall I say? You see something for the first time and you just say that this is what happens. Okay, and then through learning, you will eventually correct it. Okay, I will come to states, to equations a little later on, where we have how these probabilities are going to be corrected, and we'll also discuss this in the next class. But for the first state, it's just about I see something for the first time, and I just come up that this is what is true. Okay, I just come up with a value that symbolizes that this is what is true. So now when I have to model my entire scenario, this is my entire equation. This is just a generic equation that I have in order to represent the entire model as a combination of the initial state, the um, the transition model, which is from state to state, as well as my sensor model, which is from state to an evidence, or rather it is the other way around, evidence to a state in the real world. But remember, over here it's all about inferences. So your inferences is in the other direction. So a state leading to an evidence. Okay. But please be careful about this when you are trying to build your model. Just be careful about the interpretation about what is actually happening and what you are inferring. Okay, just be careful about that. So now the Markov assumption is it's a restricted model of the real world because we are not adding to our variables. We have a limited number of sensor evidences to consider. So it is a restricted model, but there are ways to improve upon it. We can increase the order. If you see in this diagram, it's just one state that I was concerned about. I can include the past state as well as the one before that. I can even go back to further states. So depending upon my problem, I would like to increase the order of my Markov process. And here again, this is reminiscent of the type N fuzzy sets that I was talking about a couple of classes ago, that instead of using a crisp number to represent belongingness to a set, how about adding a confidence variable to that, which is say x comma y, where y is my confidence that x belongs to this set or not. Okay, and then I add another level of confidence to that, that is x belonging to this set and my confidence on that, and how confident am I of this entire decision of x comma y taken together. So I can keep adding orders to it. I can keep adding a comma n1, n2, n3 and so on. So it's similar over here. It all depends on the problem that you are trying to model. I can also increase the number of state variables. Right over here, I have, for example, in a first order or in a hidden Markov model, actually, we are just considering one state, but I can think about other states as well. For example, here it's a rain state. I could think about a sunshine state. I could think about a weather state, and so on and so forth. Okay, it just depends on the problem. So now, if you think about, we are trying to model a dynamic system and we're trying to connect states and evidences together, right? But here we are not bringing in the semantics. Like, why is this happening, or why is that happening? We're just trying to see if these conditions are true, or if a combination of these conditions are true. Like over here, say if I have if I have more than two state variables, I will have four conditions, right? True, 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 false, false, true, false, false, like truth tables that we would draw when we were trying to design digital circuits, if you just remember that. So here, if you think we are not thinking about fuzziness over here at all. It's very crisp. It's either there or it isn't there. Like if I have two state variables, I will have a four state truth table, right? There'll be, say, RT, and say there's another state ST. So RT and ST will lead to four combinations: true, 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 false, false, true, and false, false, and individual probabilities over here of these evidences coming up over here, four combinations. So now we are not putting in the semantics over here, nor are we introducing fuzziness over here. We're just considering that whether this state exists or it doesn't. Fine. For a higher order decision model, this is a higher order that I'm talking about, because a single variable one isn't a practical representation of the world. Okay. So now if I'm considering a higher order representation or a higher number of variables, it is important that we embed the semantics in some form of the other. Right? So this is where the topic of understanding the physics of the world comes in. If you are trying to build a decision model, because it's just not if something happened in the past, it will repeat again. There are a number of factors that lead to a new state coming up, right? And it is important to embed the semantics into it. But for now, we will not consider all of that complexity. But it's a good point to remember that it's important to do that. Otherwise, there is no understanding of the world happening. If you think about it, the agent over here, this intelligent agent, is trying to design a prediction model for the future and for the other states that can actually come up, but it has absolutely no understanding of why so. Right. I'll just give you another example. See, for example, you and I are talking about a topic today, like say probabilistic reasoning. And a couple of days later, we meet again and we just pick up from the conversation. We just pick it up from here. Why? How can we do that? Because our last state was we were talking about something. You know me and I know you. We know that we have been thinking about this topic. So these minute dynamics perhaps may not be a part of a very simple model where you have a number of states and number of variables all fixed. It might be a little difficult to model this. So again, in hidden Markov models, which I said is a one-state model, what they do is they clump together a number of states into one state, which is again like granularity concepts coming in. You clump together things in order to make operation easy. So if you see, whether it be in reinforcement learning or it be this basic idea over here of probabilistic reasoning, we are constantly shuttling between shifting our granularities. At times we are expanding, we are adding to the number of variables that are there. At times we are clumping things together. So our operations itself are very dynamic. Okay. So now coming into, so now it's a good again question again to keep this in your mind about how would you model the physics of the environment or physics of interactions, the physics of psychologies. How would you embed that into models of the real world when you're trying to use a probabilistic model like this? It's a good thing to think about that. So we have two questions now. One question is these data structures and knowledge activation protocols. And another question is how would you embed semantics of the real world into your probabilistic reasoning models? Okay, these are two questions. So now again, how would you automate this process above? How would you increase the order versus increasing state variables? Because remember, I just mentioned this, that the purpose over here is operational ease. Okay, we want to arrive um, at a finite computation time, that all our calculations should end at some point in time. That is why we keep shuttling between the orders, the variables. We at times we do it in fine granularity, and at times we clump them together. So when do we do that, and how do we do that? What should be the trade-off? Okay, this is again something to consider when you are trying to design an intelligent agent, or you're trying to design a dynamic model as well. Okay. So now these are the very basic steps of inferences in temporal models. We shall, all of these steps I will explain in further detail tomorrow. Sorry, in the next class. But this is just to give you an idea of what we use our probabilistic models for, or how do we arrive at inferences. The first thing that we have is filtering. This is the estimation of xt of a state given evidences 1 to a certain t, a certain time t. So this is in a way keeping track of the current state so that rational decisions can be made. Okay, so you are basing your decisions on certain evidences that you have received till the current time to decide upon what my state should be. Okay, this is very basic. This is called filtering. And prediction is you are trying to look into the future. You take k steps forward, where k is some number greater than 0. So based on evidences that you have accumulated from the start till the current time, you try to predict what a certain state will be k moments from now, k time instances from now. That is prediction. And smoothing, that is something that is used in order to correct something that you have observed before, or not observed, sorry, something that you have predicted before. This is something, this particular step of smoothing is used to correct those. Okay. What we do is you go back in time, which is a state at time k. You use all evidences of 1 to the current time in order to kind of correct a state, or correct a prediction that you made about the state. Here, remember, it's not an here. It's actually you made a prediction of a state. If you, I'll just try to explain this a little further. At a certain point, you had made a prediction about a state. Okay. So now, as your experiences grow with time, and you actually have observations or evidences for a particular state appearing, what you do is you go back in time and you correct a prediction that you had made. Okay, so so the first thing that has happened was you made a prediction, you moved a step forward, and then actual inputs came in, and so you revisit a prediction that you made. So smoothing basically is moving forward as well as moving backward. A prediction made, which is a step forward, and then going back again to correct it based on actual evidences. Okay, so now smoothing is important, as you can very well understand. It is extremely important for modeling learning. It is something that is used for motion trajectories in order to remove jerkiness. Right. I suppose all of you might have seen these robot videos from Boston Robotics and Boston Dynamics, sorry, these companies that who are trying to teach robots to do somersaults. I suppose you have seen those videos, right? Where they're teaching robots to do somersaults and things like that. So the motion trajectory, yes, the smoothing of that motion trajectory, this is the kind of equation, or this is the kind of probability formula that would be involved in that. Okay, because first it would be very, very jerky. If you remember, yesterday Tejas too had shown an example of this of this musculoskeletal model trying to learn to walk. Okay, so it's moving forward and backward. It's taking a step forward on some prediction and then moving backward again to correct the prediction. Okay, so smoothing has a lot of role to play in learning and modeling of the real world. And the next step that we have is building explanations. So right now our explanations over here are devoid of the physics of the real world. It's like if these evidences take place, then I have these number of states, and we just wish to find out the sequence of states that have led to those observations. Okay, we have a sequence of observations, and we wish to find the sequence of states that generated these observations. There are no over here. We are not doing any reasoning in the sense of it is because of this happening. It's just we have these states, we have our evidences, and we're just trying to bring them together in order to form a likely explanation. Right? So it's like finding the argmax of probabilities concerning evidences up till time t and the states till time t. Okay, so just like the next set of words, what should be the next set of words? These chatbots, as well as these bots that answer to our questions online. All of these are trained on these kinds of models, where they build up a bag of words that follow one after the other. Here, there is no idea of context coming in, because all of these chatbots that we have, they have a very narrow environment to work in. We are not giving them knowledge of the world. We're just giving them knowledge of a certain environment, words that come up in a certain environment, bag of words that you experience within a particular context. And so what these agents are trying to do is, if these set of words come up, then my next word should be something like this. Even the GPT-3 model that in a way is giving us the feel that the world, that our chatbots can do a lot of talking and understanding and everything, that too derives from words it has learned, or pairs of words or triplets of words that it has learned from large number of text sources. There is no context coming up over here, no real context of conversations coming up over here. It's just if these set of words. Now again, if you think about it, I can just consider the word, for example, there are two words A comma B that keep coming up in a particular context C. So now if I just think about another word, if I bring into my model another word, which is say A, B, D, these keep coming up within a context C. So this is expanding my horizon of words that I consider as a sequence of words. So this is entirely that is happening in all our chatbots and all these agents that are trying to learn talking and writing. Okay, they're just building upon bags of words that come up within a particular environment. They're just building connections like that. There is no meaning happening over there. Okay, just be careful about that. There is no meaning happening. But it is our intention, it is our aim to embed meaning into these models. So again, that is a third question. How would you embed meaning into these models? How would you make these models look a lot more like the real world? How would you incorporate sensory evidences and everything and all together to build the concept of a context, which again leads to words coming up and the type of words that you would use. And context itself is a very complicated granule. How many variables would you decide in order to define a context, right? And again, these variables would be dynamic. So we can actually extrapolate all these different things that we are seeing on this particular screen. We can extrapolate it to a large number of problems. And each one is more complex than the other, and each one is more interesting than the other. It's just that. Okay, I do hope I'm making sense. I am saying a lot, I am talking a lot, but I do hope it's making sense. I do hope I can give you a feel of what this is all about and things that we are trying to achieve. I do hope it's giving you that feel. Okay. So now, once you have all of this happening, filtering, prediction, smoothing, likely explanations, we all want our agents to be learning everything. We want them to learn. We just don't want them to make predictions and stop over there. We want them to improve. We want them to learn new things as well. So now we have our transition models, we have our sensory models, we want to learn from them. We want to learn from our observations as well, which is our sampling. We want to arrive at inferences, an estimate of what transitions actually occurred and of what states generated these kinds of sensor readings, and then these estimates can be used to update the model. So this is all coming up together when you are trying to learn this model altogether. So you're trying to bring it together, these sensory inputs, these states that you are trying to define, you're trying to bring them together in order to learn, like this is how the real world functions. So again, here the problem of learning to solve murders. This is an example that I found in the book, very, very interesting. Here it says that with filtering, it will be difficult, obviously, because if you see filtering is just about a particular state, the current state, it isn't about the past. So in learning, you definitely have to look at the past. So examples over here are to solve murders. Unless you are an eyewitness, you need to infer what happened from observable variables. You need to know what a murder looks like in order to be able to converge upon the decision that you are solving a murder. If you're trying to learn to cook, you must know individual tastes and combinations thereof. So you have a bit of learning over there. It's not just tastes and combinations. You have to know about temperature conditions. You have to know about what kind of cuts can affect the taste. So there are many, many, many such variables that come into consideration when you're trying to learn to cook, even when you're trying to read. Even our bots today, almost all the available these chatbots that we have, they can all read. But if you're trying to bring in reading and comprehension together, it's just not knowing the alphabets, it's just not knowing the words, but it's just connecting the meanings as well. So maybe in some form, we can say that maybe these pairs of words or triplets of words, like I said, bag of words, they perhaps now we don't understand how perhaps the machine is understanding within quotes. We don't understand that. So maybe just for our operational ease and for our understanding purposes, we might think that these bag of words just help our bots arrive at a context. We can just come up to that conclusion for now. Right. So whatever we learn is a function of what we know now as well as what we knew, what we have learned from the past. So all of this together, all these steps together of filtering, prediction, smoothing, trying to arrive at explanations for states and evidences and states again, and learning, this entire, all these steps together build a temporal model. Okay, a temporal model meaning this probabilistic reasoning that we are trying to arrive at over time. Fine. So this is the last slide, and this again I have a certain number of questions for you to think about, for you to contemplate upon, ponder over, and we could keep revisiting these connections or revisiting these questions as we move through our classes. Fine. So this is what I had for today's class, an introduction to probabilistic reasoning over time. I can only hope that I've been able to give you a feel of how it looks like and how it could be. And from the next class onwards, we'll be moving on to hidden Markov models and Kalman filters. Hidden Markov models are when you consider one state at a time, and that too in a discrete kind of an environment. And if you want to model a continuous environment, you look into Kalman filters. Okay, Kalman filters are widely used in astrophysics and neurosciences. That's where I have found a lot of heavy use of Kalman filters. And hidden Markov models are they allow you to model any environment at a very discrete level. You're not considering continuous time changes. Okay, so we shall be moving along with these two topics in the next classes, but we have a couple of minutes before the quiz comes up. Has it come up? Is has the quiz? No, I don't think it has come up as yet. So till the quiz comes up, if anyone has any questions or any thoughts on the questions that I actually asked you, there were quite a number of questions that I asked you to ponder about on data structures and knowledge activation and the kind of trade-offs that you would do and if you were to design a model. What kind of trade-offs would you do in considering your state variables versus evidence variables? Would you increase the order with time to model the complexity? How would you do that? Right? Any thoughts, any ideas on that? We have a couple of minutes before the quiz and everything starts. Any thoughts from anyone? I just hope I'm making sense, that's all. And I suppose you can very well understand that this cannot give you a picture of the entire world, but this can just help you design an agent that can perhaps do a few things in the real world. Any questions, any thoughts, any ideas? Anything that you would like to discuss maybe, or uh, any immediate thoughts coming to your mind on these different questions that I've been asking? Anyone? Yes? Fine. So I'll stop sharing my screen then, because this is all that I had to share with you for today. And let's see if the quiz has come up. It should come up in a couple of minutes, I believe. Right. So you have the quiz on now. and you have until 9:30 to solve it, right? And I will be here on WebEx if there be any questions. Okay, okay. I'm sorry I missed this question. Can we expect it? It will be a mix. Okay, we shall have subjective questions. We shall have a few numericals, few MCQs. I haven't actually decided. I haven't thought about it as yet, but I think it will be a mix. Okay, it will be a mix of everything so that you can think. Fine. So I suppose the quiz is now active, and I look forward to seeing your answers and thoughts. And please feel free to share any questions or doubts with us at any point in time. Okay, so I'll just mute myself now for the next half an hour. And if you have any questions, please put them up on chat. No problem. Okay. Yeah. And right. So we can call it a day over here and we meet again in December. The year has almost come to an end. So right. So I'll log out now. Don't worry. Don't worry. I have shared resources for the assignment already. I shared it yesterday. Don't worry about it getting timed out. Don't worry. Just submit. How can it get timed out? You are allowed to submit. Right. Don't worry. I have shared. This is for Aditya. I have shared resources for the assignment. Excuse. Whatever they just put up yesterday, they are all up there. Oh, that is true. We have raised the deadline of the assignment. The deadline of the assignment is now the 10th. Okay. This is for Nikhil. Can you please tell me your email ID once? Right. The deadline of the assignment is now the 10th. You have 4 more days. Okay. Just give me a minute. I'll let you know if I have received assignment. Yes, this is for Nikhil. Your response has been recorded. Yes. Don't worry. Mm. Right. Aditya, have you found out all your... Very good, very good. Yeah, don't worry. That's strange. Ritvika, can you just share your email ID with me once? I'll just check if I have received. No, ma'am, can't find. Okay, I'll just give you a minute. Yep. Your response is coming, Ritvika. And Aditya, I think I put it up yesterday. It's on Google Classroom. If you see, I shared this. Now, where did it go? I just put it up yesterday. I put up the chat and everything on Google Classroom. Fine, I'll check it out. I'll look into this. Right. I will. This is for everyone. I clearly remember putting up all the resources up right after the class got over, but now I can't find it on Google Classroom. So I'll just check it out. Okay, I put up the chat transcript as well since the recording wasn't available. Fine. Don't worry, I'll check it up and I'll put it up again. Oh, right. Okay. I forgot. Thank you, Nikhila. I had forgotten what I had written. Right. And I've also put up the chat transcript for the earlier class, right? For lecture 13. That is available as well. Yeah. Fine. Thank you so much, Nikhila. Yes. Right. So it's and the chat transcript of lecture 13 is also available, I suppose. Right. This is right. The chat is also all up there. So I suppose it's almost 9:40 and you don't have a class, but you will definitely have work to do. So I just hope I'm making sense in all the class. I do talk a lot in the classes, and I just hope I'm making sense. Please feel free to ask questions and get back with your thoughts and ideas and questions. Okay, right. So do have a happy day on and a lovely week ahead, and we meet again in December. Right. And you share any practice on numericals to run these RL algorithms. I look into this a little. I'll look into it. If I have, I'll put it up. Okay. I'll definitely look into this. I will look into it and I'll put it up. Right. So I think we can log out now and oh, thank you everyone. Thank you everyone. So I suppose we can all log out from here and get along with other work and we meet again on Saturday. Yes. Bye bye everyone. Have a happy day and a lovely week ahead. Bye bye.